All right, let's talk about good code. So what is a good code? A good code is one that is readable and scalable in terms of speed, time complexity, like how fast your code runs, and also in terms of space complexity, memory usage, like how much memory it needs to run. Why it is important at the coding interview, especially at the big tech companies like Google, Facebook, and others, is because they want to know if you already know these things. And if you can show them that you can save them time and memory resources, which both of them are really expensive, then you have your foot in the door. And also, if you want to become a good engineer, because this is a pillar for programming, and if you want to become a good engineer, you got to know these things. A good code works longer. It has a long lifespan. For example, if you have 100 users to your website or app, and you write good code, so even if you have like 100,000 users, your code will still work because you have already thought about making it efficient. All right, let me show you two functions. They both do the same thing. So if we console log add up to 10, we get 55 as the output. So let's now take a look at the second function. This one uses the mathematical formula. It's not using any loop or anything. And if I provide 10 as the input for this function, I'll get the same output. So they do the same thing, but it is implemented differently. So which one do you think is a better code? Is it the first function or the second function? Well, there is a way to time the function, so whichever takes less time, we can say that's the faster code, that's better, right? So let's time the first function. I provide a large number, like a billion over here, and I'm using the performance.now from Google Chrome to figure out how much time this function takes. So let me run this. And it's going to take a while. As you can see, it takes up 0.881 second. And if I try to run it again, you'll see a slightly different number. So now let's see how much time the second function takes. So if I run this one, you can see that the time it took was 0 seconds. Like the number is so low that, you know, compared to the other function, it's really low. It doesn't, it rounds down to 0 seconds, or sometimes very small number like this. So, but you can see that every time I run it, I get a slightly different number, and that's even on my own computer. It's not, and I have like a 32 GB RAM, and it might be different for your computer, or if the server that we will be running this code on. So how we will determine that which code is better without using such a performance.now, because it gives us a variable different output each time. How can we make sure that this, the code is better, or what is the time complexity or the space complexity? This is where the big O notation comes into play. When we talk about big O in the scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm or function slow down? If the list of input increases, how many operations do we have to do? That's all it is. This is what we call the algorithmic efficiency. So when we grow bigger and bigger with our input, how much does the algorithm slow down? The less it slows down, or the slower it slows down, the better. I can see we have O of constant 1 here, O of n, and O of n squared. This is excellent, and this is good, fair, and this is bad. This is horrible. You don't want to be here. Anyways, now let's see how we calculate these values. How can we determine where in this complexity chart which line does our code fall into? Now let's calculate the number of operations for the first function. As you can see, this is one operation, this is another operation, this is another operation, this is another operation, this is two operations, one is assignment, one is adding up the numbers, and here's another operation. But what matters here is the number of input, which is n, right? So if that increases, this also increases, the number of these operations increase, right? So we can simply say that this is a big O of n. Why? Because this is 10 over here. We can make it like a larger number. So the bigger our input becomes, the time complexity for this function grows like that. So in the complexity chart, if I show you, which one was it? This one. In the complexity chart, this falls into here. You see, this is O of n, and this is how the number of function grows. The time that it will take for the function to run will grow in such a line, which is not very bad. So now let's take a look at the number of operations for the second function. As you can see, this is one operation, this is two operation, and this is three operations. So if it is 1 plus 1 plus, so it's 3, right? But that's not significant, like 3. We can just change that to make it 1, a constant of 1. So we can write the big O notation for this function is to be O of 1, because there's no loop in here, and it does not grow like the one that I showed you before. So O of 1 falls up here. It's a straight line, and it's excellent code. Log all pairs. So what does this function has? It has a nested loop over here. If I run this, it logs out the pair from this array. Since this is a loop inside of loop, we can say the big O notation for this one is O of n square. And to show you the time complexity chart for this one is here. So when you're using a loop within the loop, this is how the number of operations will grow, and it grows exponentially. So that's another example for the big O notation. So far we've looked at the time complexity functions, and we now know what can cause the time in a function, that is operations, which is the addition, subtraction, multiplication, and division, comparisons, loops, for, while loop, and outside function calls. Now let's take a look at the space complexity. What can cause space complexity in our code? That is variables, data structures, function calls, and allocations. Let's take a look at an example. Now we're not concerned about the time complexity, the speed of the function. We want to know what the space complexity is for this function. So what do you think? As you can see, as we already discussed, that variables cause the space. So we only have one variable. So the space complexity for this function is O of 1, right? Let's take a look at another example. This is a function that takes in an array. So the bigger the array input, the more space we're going to need. So it is directly proportional to the input, which is n. So the space complexity for this function is going to be O of n. Alright, we've reached to the end of the video. We've covered the common big O notations. That's it for today.